some different conditions. So first of all, I want to be sure about the terms here. So do you have do you feel the distinction between the circuit and the cycle? So there is like some different notations here, like circuit, cycle, path, and trail. And in different books there are different notations, so I need to be sure that we.
Hello, sir.
Hello, Daniel. That we
How are you feeling, sir?
Better than the previous week. Thank you.
No problem, sir. No problem.
So do you feel the distinction between these terms? What do you mean by circuit, cycle, path, and trail?
Hello, sir.
Hello.
Sir, the only two that look familiar are cycle and path.
And what do you mean by them when you use them? What is cycle and what is path?
Cycle means that there's more than one way to reach a node, or maybe we can say that if there are v vertices, there are more than v minus one edges and it's connected, or
Yes.
something like that.
Yeah, usually you look at the sum. So if you have graph G, then you can just try to build a long connection with use of edges. So you look for the some sequence of edges, and maybe we'll start with vertex here. So we start with vertex, then we have edge, then we have vertex, then we have edge, and so on. And the sequence means that if I have some edge, then it places between vertices that are connected with this edge. So this is just like vi plus 1. So we have like vertex v1, vertex v2, and edge e1 connected them. Then vertex v3 and edge e2 between v2 and v3, and so on. So the last will be like vk plus 1, and he will have like edge ek here. And we can put some restrictions because sometimes we want the edges to be distinct, and usually we want the edge to be distinct, but we can also put a restriction that we want vertices to be distinct. So if edges are distinct, usually it calls trail, but in some books it's called path. And if vertices are distinct, it usually called path, but it also called simple path. So
Sir, so path is not from path graph, like the tree with v minus 1. Isn't path from path graph?
we called a path in graphs like the sequence of the vertices that will connect with the edges, but we need to put some restrictions. So so if we have not tree but like just one line with edges between them, this we can call a path.
Okay.
But for example, if we have a tree in form of a star, like this one, then we cannot have a path longer than 2. So maximum that we can have is just the connected center with one vertex on one board, on with two different vertices on the left and to the right, for example.
Yes, sir.
So here the length of maximal path will be equal to 2. This definition is okay, yeah. So but if you want to have a cycle structure, so here if let me continue here. So if vk plus 1 is equal to v1, we talk, so the first and the last are the same. So we have like this structure. We have v1 connected with edge e1 with v2. Then we have edge e2 with v3 and so on. And here we have connection with v1. So edge ek connected vertex vk with v1. We can call it a cycle or a circuit. And the difference is the same. So we call it a circuit if all the edges are distinct, and we call it a cycle if all the vertices are distinct.
I'm sir.
Yeah.
This looks like a normal cycle graph. So my question is, what exactly do you mean by distinct? So we have a set of vertices. So that means all the vertices in there are unique, right?
For example, if you have like two triangles, then we can build a circuit here like this one. But it will be not the cycle because one vertices are so we made these vertices 2 times during our cycle. So here, if you want to write this as, so we can, using our definition, we can write the circuit like here, but v3 and v6 will be the same vertex. Okay. So this is a circuit, but it is not a cycle because one vertex we meet this 2 times, so it occurs 2 times in our sequence of the vertices. Okay.
Okay, sir.
Circuit, not a cycle. And in some books you may I don't know how do you define them, and if there was any difference when you just define them in the Alexander Schultz in the first part of combinatorial graphs, because in some literature also they can call, like, circuit can be called a cycle, and the cycle can be called a simple cycle. And for example, in some Russian books they're usually called, so there are like different notations, so they call not circuit cycle but cycle and simple cycle. But here I want to give like these definitions because I think it occurs in many more books, and I think it's more useful than the definitions. Okay, so what you want to know, if the 2 main questions we will discuss in today is, can we can we build a circuit, or can we find a trail that contains either all vertices or all edges in my graph? So the first question is is one of the first questions in graph theory, and the question about bridges of Königsberg. So there was the mathematician Euler lives in Königsberg, and once he asked himself a question can he? There is a river and some deltas of the river in Königsberg, and he asked, can he traverse all the bridges such that he not traverse the same bridge 2 times, but he traverse all the bridges. And I just write a map for you. So there was like one island, two island, here, and the bridges like here, here, and here. So does we have? So we have like we can ask two different questions. So do we have a trail that connect all these vertices so we can cross all the bridges, such that we cross all the bridges and we didn't cross the same bridge twice? So we want to cross every time we want to cross the all these bridges, and every bridge crosses only once. And we can try to, so if you try to build some trails, so for example, start here, then we can cross here, then for example here, and no, we stop here, but we didn't use the one bridge left, and we can try and to construct another trail, and again one bridge is left. So can we prove that there is no such covering all the bridges? So how can we determine this problem? So if we have graph G, if there is a trail which consists of all possible edges in our graph, of all edges in G, and if there is, this trail is called Euler trail. So Euler trail is a trail covering all edges, and we call another circuit is circuit also covering all the edges. Do you have an idea how to prove that we cannot have Euler trail in the graph that I write it just above? So we can write the picture. So we have like 4 vertices, and we have we can connect them by these edges. Again, I just don't know if you have in your graph theory, like how do you define a graph when you have multiple edges between the same vertices? Multigraph or something like that? Because there are again different definitions. Usually when we say graph, we usually don't have like multiple edges, or like, so we can move from the edge to itself, and the graph we can have multiple edges between the vertices. They're called like multigraph, or you don't have this notation in the graph theory.
When we have an edge going to itself, we call it a loop, and yes. Then for when we have multiple edges between two of the same vertices, I think we call it a multigraph.
So multigraph is where we can have loops and multi edges in the vertices, yeah.
If we have multigraph, is just when there's more than one edge between the same two vertices. We didn't really give a name for loop. For when there's loop, I think we just said that it's not a simple graph when there was a loop.
Okay. So here, this problem we can talk about multigraph also, because it doesn't matter how many edges do we have between the same vertices, and also we can add loops. I don't think that it is. So in this problem we have a multigraph, but I think you can forget about. So it is easy to see that my proof doesn't need to. So in my proof that doesn't need to be only one edge between vertices. So you can all the proofs you can easily easily prove it by multigraph, but I will set about usual graphs. Okay, so do you have an idea how to prove that there is no other trail here? Oh, you didn't see this, so this problem didn't appear, so you didn't solve this problem earlier. No. So let's start with the Euler circuit, because yeah.
So based on my guess, maybe if there are even number of bridges, maybe.
Yeah.
Would
So
be able to.
we start with Euler circuit because it is simply to see what happens here. So if we have, so suppose we have a graph, and somehow we have an Euler circuit there. So we can just, so maybe I will write this. So I will write arrows just to show how I construct my Euler circuit. So I just like.
So it's just a director graph.
Yeah. No. Just again, we can look at the directed graph if we so we can ask the same questions about the directed graph, but now I just want to so if I so it's something like here. So if I just construct, I just try to write some Euler circuit here. So this curve are just the edges between vertices. So maybe I will write this more accurately. Maybe we'll write here so we have no double edges. So if I have another circuit, you can see that each vertex has even degree, because if I have another circuit, I pass all the edges. So all edges are represented in my Euler circuit, and in each vertex I have edge that I come in and then I come out. So if I start here, for example, I come here to this out, then in, out, and so on. So in every vertex, I have one edge coming in, one edge coming out each time I pass this vertex. So we have, for each vertex, we have even number of edges that I use when I build a circuit. And so each vertex must have the same even degree. Each vertex and the best news is that it is really the criterion for the graph to be Euler graph, so to have Euler circuit. And so the theorem that we can prove is that graph G without isolated vertices has an Euler circuit if and only if, first of all, it is connected, and second one, each vertex has even degree.
Sir, so in the bridge example that you drew, if we were able to cross all the bridges with that, it will be called the Euler circuit.
Yeah, but when in the bridge problem, we need to build trail, not a circuit. We can we can have a trail also.
Okay, sir.
And so maybe we can build a circuit, but we can build a trail, because in trail we have two vertices on the edge that that can not be even. So for example, here I can just add like one edge here and one edge. So start from here and ending like here, and so we can have like two edges of odd degree. And this graph can have another trail. But in the bridge problem, we see that if we find all the degrees, we have 4 here, 3 here, 3 here, and 3 here, and we have 3 vertices of not 4, 5 here. Sorry, I mistake. And we have 4 vertices of odd degrees, and we will prove that we cannot have, if we have 4 vertices of odd degree, then we cannot build Euler trail, because Euler trail can consist not if so if a graph have another trail, then we have no more than 2 odd vertices of odd degree. Okay, because
Okay, sir.
if for Euler circuit we have the criterion that all vertices must have an even degree, then for the trail we cannot have more than 2 vertices of odd degree. And if we prove that, then we can solve the bridge problem. So here I mentioned the isolated vertices. Of course, if you have isolated vertices here, you can just forget about them, because we cannot, we don't have any edges between them. So for example, if a graph has no edges at all, an empty graph, then all the vertices have even degree is equal to 0, and of course it has an Euler circuit. But to be so we can drop out all the isolated vertices, forget about them, and look only on the connected part, connected component, the one connected component of the graph. Let's prove the theorem. So idea is very simple. So okay, so first of all, we prove it from the other side. Just before I explained. So if we have another circuit, of course, graph G must be connected, and of course the vertex has even degree, because if you look at the Euler circuit, then in each vertex we have when we meet this vertex, we come in and come out from this vertex, and so each time we count 2 of its edges, and so at the end of the Euler circuit we count the even edges of this vertex. So for each vertex we have even degree, and so maybe I will just write it here. So we prove it. So all we need to prove is that if G is disconnected and each vertex has even degree, then we can build an Euler circuit. And idea is the following: we take arbitrary vertex v1, and we choose arbitrary edge from this vertex to another vertex v2. Then vertex v2 have an even degree, so it have at least one more edge. That is not so. From we have at least one more edge going from this vertex to another. So, for example, it is E2. We come to B3. Again, it has at least one edge to another vertex, and so on. And so from each we can continue this path because each vertex has an even degree. So if we have like we come into the one edge, of course we have at least one edge to come out, and so we have the finite number of vertices in graph. So sooner or later we will meet the vertex will already be when will already be. So for example, here we can just go to the VK and then we come to the vertex where we already been before. It means that we have just a cycle in our graph. So there exists a cycle in our graph. And if we have a cycle, so if we just cut all these edges from our graph, so we forget about these edges, then all degrees of all these vertices in these edges will be lesser by 2. So for all these edges, all these degrees of these edges will be lesser by 2. And so the graph that left is, so if we forget about these edges, then the new graph, again, all these vertices has an even degree. And again, we can find a cycle in this graph. And so we can just, so by induction, we can prove that our graph can be described as non-intersecting cycles. And then we can just cut them, glue them together in one bit circuit. So if we have, so if our graph, we represent it as like different cycles, then we can just start on the other cycle and do the same procedure. We just if we have a vertex that is containing other cycle, then we can use the cycle and go along it, and then continue with our cycle. And then if you do it in a proper way, then we will have an error circuit. Oh, this is idea, and then if you have this idea, we can prove this part of the theorem. So we just need to say the correct words here. So for example, suppose that we find the circuit of maximal length in our graph. That we find a circuit. So maybe I need to formulate it. So suppose that we already find is circuit containing maximal number of edges. Containing maximal number of edges. If we collect all edges, then this is okay, and the theorem is proved. If it is Euler circuit, then we prove the theorem. Otherwise, we have some of edges that not contained in our circuit, and then if we consider the graph without these edges, all vertices in G prime equal to G without these edges has an even degree. So again, we have a circuit. If we forget about these edges, then each of vertex will have like we can subtract 2 times the number of vertex appear in our circuit, and we'll have the new degree of this vertex will be also even. So all vertices has an even degree, and by our lemma, we have a circuit in this graph. So we can also suppose that all connected components by induction hypothesis has an Euler circuit. So we can prove this this proposition by induction, and if we have like 2 vertices or like 1 or 2 vertices, then okay, of course we can construct the Euler circuit. So if we forget about this maximal circuit, then in all connected components of our graph, we can find Euler circuits. But it means that our circuit intersects with some other circuit. So since graph G is connected, then in each connected component we have at least 1 vertex from our Euler circuit, from our circuit. So we have like this is, and Euler circuit contains all edges in connected component. It means that our circuit intersects with another circuit, and if it's really true, then we can glue them together. So for example, if we have like 2 circuits that are intersecting to each other, so will be, for example, our circuit V1, V2, V3, Vi, and Vk here, and here we'll have like W1, Y1, Y2, Y3, and so on. And so we can just construct a new circuit that are going through all these edges. And so we have built a circuit that has more number of edges than our circuit. And it's contradiction because we consider the circuits containing maximal number of the edges. We can construct a circuit with more number of edges. Contradiction. And so we can construct the circuit that contains all the edges, and it will be the Euler circuit. Is it clear for you, or you have some questions?
Sir, honestly, I really don't understand what we just did. So,
well, I can have maybe I will have a commentary, and you will understand how you construct another circuit or a circuit. So
yeah, okay, sir.
you just find the you can find any circuit that you can have. So for example, this one. So you find so again we start with 1 vertex, then you choose any edge that you can have in this vertex. Then again you choose the any edge that you want from the next vertex, and so on. And you've somehow constructed a circuit starting from arbitrary vertex that you choose. that if you have this, then if you cut all these edges from the graph, the graph will be can have like some different connected components, because when we lose some edges, if our graph was connected, then if we lose some edges, then the graph can be disconnected. But we have like connected components. Do you know what connected component is? Or you don't familiar with this concept?
I think it's like a subgraph of connected, which is connected to connected subgraph, something like that.
So what is connected component here? For every graph, we can have like so if we choose any point, we can look at all points which is connected with this vertex. So if we choose any vertex, we can find all the vertices which have path with our chosen one, and the set of all vertices that are connected with one of them is called the connected component. And all graph can be described as a disjoint union of this connected components. Okay.
Okay, sir.
If you need, I can prove it. That so. I just need to look how to call this term in English. It's called, so do you familiar with the equivalence relations? Or no?
What relation, sir?
Equivalence relation. No?
No, sir.
Okay. So we can just okay. I will tell you somewhat about connected component if you have not meet this term. Connected component. So we can say that we have two vertices and they are equivalent to each other. V is equivalent to the tilde if there is a path between them. So it means that if we start from V, we can get to the V tilde somehow. And this relation is so-called transitive. So if V is related, so if V is we can disconnect it. So if V is connected with V tilde and V tilde is connected with V double tilde, then of course V is connected with V double tilde, because if we have here like some path, we can we can construct a path from V to V double tilde, and so we can just if we have graph G, we can denote by KV set of all vertices that are connected with our fixed one. And the main proposition here is that if we have like two different vertices, then either they connected, so all vertices that connected to one and the two are either coincide or they're not intersect to each other. So if I like choose one vertex and see which vertices are connected to it, and if I do this to another vertex, either the set are coincide or they're not intersect to each other. and this is not very hard to see, because if they have like some so if they have some vertex in intersection, then V is connected to V double tiled connected with V tiled, and so by the transitive relation, we can build a connection between V and V tiled, and if it's so, then if they are connected, then each vertex that is connected to V tiled is connected to V and vice versa. So we'll have them in like one set of connected vertices. And so our graph, it means that our graph are disjoint union of these sets of KV. So G can be, all edges can be represented as disjoint union of this connected paths, which is called connected components. Connected components. So if you want to construct them, we just look at the graph G, we just choose the arbitrary vertex, and then we look how far can we go from it. And so we have like one connected component. Then we choose one vertex except from one that we chosen before. And so again find all the vertices that connect with this one. And we find the second connected component, and so on. So when we can just look at the graph as the union of these disjoint connected components of graph. Okay?
Okay, sir.
Okay. So here, after I find the circuit in my graph, when I forget about these edges, then my graph can. So it was connected, but now we can have some like some different connected components. So we can go from one component to another, because when this, so not using this circuit that I find. So for example, I have like two parts here and here. So from part one, I can go to part two, not using this circuit that I just already built. And so when I forget about these edges, these components will be disconnected. But in each connected component, they contain lesser number of edges, and so by induction hypothesis, I can build an Euler circuit there. So in each of this component, I have another circuit, and if it's so, then I can glue them together to get one big Euler circuit. How do I do that? I just start from my circuit, and if I meet one of the vertices from the connected component, then I use Euler circuit to go through all the edges in this connected component, and then continue to going from my the circuit that I find. Then I meet another connected component, and then I just go through all the edges in this component, and so on. And after I go over all my circuit, I will count all the edges that I have in my graph, and so I build another circuit in big graph. And this is the idea of how to find an Euler graph, an Euler circuit in graph. Okay.
Okay, sir.
So I just described the algorithm how to find an Euler circuit. So if you have like some graph and you know that there is know that it's in degree, you just can just choose circuit, then choose another circuit, then build like I don't know, another circuit, and then just glue them together. So you start from, for example, this one, and you goes like this one, but this one, I just forgot about how it gets through this one and this one. And so we get an Euler circuit in your graph. So the corollary, I can just give criterion of how to get the Euler trail in our graph. Graph with no isolated vertices has an Euler trail if and only if G is connected, the number of edges of odd degree edges is no greater than 2. And of course, if you have so if you have an Euler trail, then the number of odd degree edges is not greater than 2, because if you so what's the difference between Euler trail and Euler circuit? If you like look at Euler trail, we have two options. Either Euler trail is just an Euler circuit, but just forget about this. But we forget about that it can be trail. So we start and ending in the same vertex here, or we have some different picture. So we have like some edge to the start, and then we go across our edges and finishing somewhere on the in some other vertex. So for example, finish here. And this happens when we have exactly two vertices of odd degree. Oh, sorry, I find these edges and I need to find these vertices here. Vertices. So here we have like this one and this one. I have an odd degree. And if it is so, we can just connect them. And if we connect them, then we'll obtain a graph where all vertices have the even degree, and then we can build an Euler circuit, and then we just forget about this edge, and we will have another trail here, as in previous theorem. So all we need to do is just, so if we have another trail, of course we hear that there's only two options, and in each of these options the number of odd G is connected and the number of odd degree vertices is not greater than 2. And if we have connected graph with a number of odd degree vertices not greater than 2, so if it's 0, we just build an Euler circuit and just make it path, make it a trail. And if we have exactly two vertices of odd degree, we just build a new edge, connected them, between them, build an Euler circuit, and then we forget about this edge, and we will get an Euler trail in our graph. And so, for example, in the bridge problem, we have exactly 4 degrees of 4 odd degree vertices, 5, 3, 3, 3, and so we can have another trail there, and so we cannot cross all the bridges such as we meet all the bridges exactly once. Okay, and I want to discuss some additional. So maybe how can we use this idea to in like some algorithms theory. First of all, we cannot. So we have duration of this theorem on the oriented graphs. You call them directed graphs, yes. So if if we have an rotations of all the edges, can we again build a circuit? It means that all times we use we go from one edge to another under these arrows on these edges. So for example, we have like some directed graph, and we want to find is there a circle that contains all edges. And of course, here we have different types of degrees. We have in degrees and out degrees. Do you have like special denotation for them when we discuss directed graphs in the first part of the course?
Not really, so we just call them outgoing edges and incoming edges.
Okay, yeah. So you can calculate all the incoming edges in our vertex and outcoming edges in our vertex. So in degree is the number of all incoming edges, number of all incoming edges, and his number of all outcoming edges. Maybe I can forget about also. Okay, can someone give me a criterion for existence of Euler circuit in directed graph? So how can we put it here? I can start. So again, a directed graph without isolated vertices has an Euler circuit if and only if G is connected. And what was the second condition?
So maybe in degrees equals to out degree.
Yeah, of course. In degree is equal to the out degree for all vertices. Of course, if you have an Euler circuit, then if you have incoming edge and you have outcoming edge. So if you go into the vertex, you need to go out. So if you have an Euler circuit, then in each vertex we come in and come out. So we like in out in out in out. And it means that in and out are equal to each other. So if you forget about the direction, then we'll have the degree of even. So this vertex can have in even degree because in is equal to out, and this is transformed into this equation here, and the proof is the same. So you just if you have you can prove it by induction, and so if you have like big graph G, you can find the circuit there because I can start from each vertex, go through the edge, and then if in is equal to out, then I have at least one edge out of this vertex, and then I go into the other vertex and so on. So I can build the circuit, and then I can forget about it, look at the connected components, each connected components. We forget, so we just draw out from each vertex, we draw one in edge and one out edge, and so the alternate components satisfy the theorem, and so we can build a neural circuit there, and then we can construct the Euler circuit in our graph. And the same will go to the Euler trail. So we have like only one. So all the vertices must have equal in and out degree, and one vertex can have like 1 degree out. So his out degree will be in degree plus 1, and so one vertex will have, if one vertex have like 1 out degree, so with one more in degree, and one vertex have one more out degree, then we have another trail here. How can we use it? For example, suppose we want to fix the alphabet of zeros and ones, and we want to construct, for example, the sequence of zeros and ones such that each possible triple of this of the zeros and ones occurs in our sequence. So we have like so for example we have like 8 possible combinations of zeros and ones, and I want to write the sequence of zeros and ones such that each sequence appears into my sequence, and I want this sequence to be the minimal possible contains minimal possible number of elements. So for example, if we have like for a sequence of 2, I can just try to build. So I have start with 0 0, then I go 1. Oh, here I have like 1 1, and then I go. So for example, if I go like 0 1 1 here, so all possible 2 subsequences will be 0 0 0 1 1 0 0 1 and 1 1, and we have here we see here that 0 1 is occurs 2 times here, and we want to be this sequence as little as possible. So we want to have the minimal number of elements in our sequence. So so if you want to construct our sequence, that we need to do another way and go like this one. So if we like consider 0 0 1 1 0, then we have like all possible, so all subsequences of length 2 is equal to 0 0 0 1 1 1 1 0, and we have each of them occurs only once in this segment. Do you understand the problem? So the problem is, can we do the same for the length 3 or more the length of zeros and ones? Okay, so maybe I will give you like 3 or 4 minutes, and you trying to find a sequence for the length 3. So I need to unify the sequence of zeros and ones such that each subsequence of length 3 is occurs only once. So we have only 1 0 0 0, only 1 0 0 1, and so on. So you can try it by yourself. So I already find it for the length 2, and maybe you'll try to find the same for the length 3. I will give like 3 or 4 minutes, and then we'll discuss how to do it using the graph theory. Okay? Do you understand the problem?
No, sir.
Okay. So I need to find to find the sequence of zeros and ones such that each subsequence of length 3 is all subsequence of length 3 is different, and each subsequence of length 3 is occurs there. So
Okay.
So here, for example, I have 0 0 1 1 0, and each of subsequence of length 2 is different, and all of them occurs. So we have like four types of sequences.
Yes, sir.
And so, for example, we can calculate what is what will be the length of this sequence. So, for example, here we have 4 types of sequence, and we have so we need to have length 5. And here we have like 4 types of sequence, and so if we start from 1, I think the length will be 10, because we like here like have 1, 2, 3, 4, 5, 6, 7, 8, and so like it must be collected of length 10, and so he will be like 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 1, 1, and so each of them can be occurs only one. But here it is wrong seconds, because for example I have like 0, 0, 1 occurs 2 times here, and I need to be them occurs only once. Okay, so I'll give you like 5 minutes to think, and then we can discuss.
Okay, sir. Um, so I think I have a formula and a sequence.
Okay, could you please tell me the sequence?
1 0 0 0,
Okay,
1 1 1,
okay,
0 1 0.
okay, 1 0 0 0 1 1 1 0 1 0. Yeah, okay, so I think this is
And
correct
sir,
one.
I think I have a formula to find the length of the sequence for any number that we want.
Yeah, but wait, sorry, no, it's not updated. Yeah, but do you have an idea how to construct this sequence into arbitrary number of elements? I can. So I understand that you can just. So the length will be just 2 in the nth power plus like n minus 1, something like that.
Yes, sir. 2 raised to the power n plus n minus 1.
Yeah, but we can also discuss the algorithm how to. Now I'll discuss the algorithm how to find it into. Okay, so this is the sequence to find, and now I'll explain how to what. So the idea of construction is similar. So it works for arbitrary length of the sequence, or we can add like consider not alphabet of 0 1 but 0 1 2 or so on. And here is the trick. I will just draw some graph, and this sequence will be corresponds to the Euler circuit in this graph. So let's start with the first one with length 2. It will be the simplest examples that we have. And so first of all, what is the vertices of my graph? The vertex of my graph is just the sequence of lengths of n minus 1. So if I want to construct it, the total subsequence of length n's occurs in my graph, I will have my vertices as all the lengths, all sequences of the length n minus 1. So if I have n equal to 2, then here I start with all the sequences of length 1, each just 0 and 1. And for example, if I want to construct my sequence for the n equal to 3, then I need to have all vertices corresponding to all the sequences of length 2. And then I will write an edge from one vertex to another if it where it will be the beginning and the end of the sequence. So the edges will be sequences of length 2 or 3. So here I'll have like the length 0 0. So if it starts with 0 ends 1, it will be edge 0 1, 1 1 from here to here, and then 1 0 here. And here I'll have the same idea. So if I connected two vertices with one another, then I have the starting sequences from the first vertex and the ending from the other. And so if they concert together, then we'll have the sequence of length 3. So I have the vertex from 0 0 to 0 1. I have vertex from 0 1 to 1 0 will be 0 1 0. From 1 0 to 0 0 it will be 1 0 0. From 0 1 to 1 1 it will be 0 1 1. Here will be the vertex 1 1 0. And I have like two loops 0 0 0 and 1 1 1. Have like 1 2 3 4 5. Like here I have okay, and here I have one more edge like 1 0 1, and I have exactly 8 edges here. 1 2 3 4 5 6 7 8. And so I just have a graph in which all edges that I have corresponds to the sequence of length 3. So if we have an Euler circuit here that contains all the edges, and look that if I started from one edge and continue to the next edge, then since we have, so this 0, 1 will be the ending for the first one and the beginning to the next one. And so if we look at the Euler circuit in our graph, then we can construct the sequence that we needed. So for example, here, if I look at the Euler circuit here, I can start it from like 0, 1, then it will be 1, 1, then 1, 0, and then 0, 0. And here I have like, for example, I can start from 0, 0. So I'll have like, I can find the Euler. Actually, I need another trail because I look at this sequence, not so this is not circular sequence, but just another sequence. But so I'll need the trail. So I need, so for example, if I start at 0, 0, I go to 0, 1, then I go here, 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 and here. And so I can just find the sequence. So it will be 0, 0, 1, then 0, 1, 1, then 1, 1, 1, then 1, 1, 0, then 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, and 0, 0, 0. So for example, your solution is like another trail here. So I start with 1, 0, 0, goes through this one, then go to this one, then go 0, 1, 1, 1, 1, 1, 1, 0, 1, and this two. And so I can do this for arbitrary sequence of n. All I need to do is just start. So I find like so I just can find another trail and in my graph, and then I just write the sequence. So it doesn't, so if for example I have, if I need to do this for the sequence of length 4, then I just write all the vertices will be sequence of length 3. There will be like 8 of them. And then again, all my edges will be the sequences of length 4 that are connected. So the first part, the first 3 symbols is the out edge, and the last 3 will be the in edge. For example, from here we'll have like 0, 0, 0, 1, and here I have like 1, 0, 1, 0, 1, 0, 1. And so if I write all the edges, they'll be like exactly the 16 edges. And so if I have the Euler trail, then I prove that I have this sequence that contains all subsequences of length 4 exactly once. So all I need to do is just count the in and out degree of each of my vertices here. But for example, here I can see that if I have like vertices 0, 0, then I have 2 edges coming in. So I can from 1, 0 and from 0, 0, and have 2 edges coming out for, so because I can connect this with 2 other vertices here. It will be 0, 1 and 0, 0. So for each vertex, I have 2 in and 2 out degree, and it's exactly the criterion for the Euler, for the graph to contain the Euler circuit or Euler path. And so I have another trail, and so I have another trail here, and so I can connect them and write the sequences containing all the subsequences of fixed lengths exactly once. Do you understand what I'm saying? So have any questions?
Sure. So what is the number of possible sequences for?
It's a tricky question because they will have like many of them, because so all I just proved that I can construct one of the sequence, but of course this if you want to find all possible sequences that we have, that we'll need to use the structure of this graph, because we want to know how can we connect it one of them. The first, the maybe simplest question that I can answer is, do we have like a simply algorithm to construct? Because if you have like big graph, finding the Euler path is not very simple, because I just I know that I know that it exists, and I know that I constructed just going through edges in and out. But do I have like a simple rule that I can just that I can use, and it uses this rule? I can write the sequence like in 10-15 seconds. So I just need to use this. So can I just use this rule? And I think I can try to explain one of this rule to you, and then I think we'll be finished for today. So give me just 1 minute. I just need to be sure that I find the right algorithm. Yeah, so so suppose we started with the rule 0 better than 1. So we do this tricky idea. We started from so if we want to write the sequence that contains all the subsequence of length k, then we do the same. We start with the k once, and then we all the time we put 0 if we can put 0. But if we cannot put 0 because the new sequence will be occurs more than the new sequence already occurs in our sequence of length k, then we put 1. So we also all the time we put 0, except for the cases when we have like we will meet the sequence already. So for example, if we started with the 2 1s, then we go to zeros, and then we cannot go to the third 0 because it will be contain the same sequence here. So we put 1 here, and so we constructed the sequence for the length 2. And for the length 3, we start with 3 1s, then we put 0, then we put 0, then again we can put 0, but then we cannot put 0 because it already occurs 3 zeros. So we put 1, then I cannot put 0 as we can. We cannot put 0 again because 1 0 0 is already occurs here. So we put 1, and we can put 0 because we already have 1 0 0. So we put another 1, and so this is all. I finished, and I have all the sequences of length 3 in my sequence. Do you understand how do you use this rule?
Sir, so we have to check.
Start from the key ones, and then write 0 if we can. So it not already occurs in the sequence. Yeah.
Yeah, sir. So we have to check if the sequence already occurred before we put a 0 or 1.
Yeah. So we just try to put 0. If we can put 0, okay, put 0. But if we can't put 0 because the new sequence of new key, the sequence of length k, is already occurs, then we put 1.
So how do we know the number of ones to put? Okay. Sir.
I don't prove that that I have the sequence that we need. I just give you the algorithm. The algorithm
Yes.
is simple. We just put k ones and then put zeros if you can. If you can, we put ones. Of course, by construction, we see that each of the k subsequence will be different because we just use in construction. Okay, if we see the sequence that we already have, then we do not use it. But the tricky will be the proof that all of them occurs here, because for example, we can stop earlier and we cannot move. We cannot write the next 0 or 1 because in 0 and 1 already occurs here. But maybe we didn't we didn't meet all the possible sequences. And so to prove it, we already need to look at this graph that so maybe I will give you the idea, and then I will finish for today, and then we can discuss it next time if we have. So, for example, here we can look at what happens if we started from. So we can see it and our edges here. So we have like edge here, 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 and then here and here. And we can look at the edges that appears if we just add one. So the edges that finish on the one. So what edges are ending on the zeros and what edges are ending on the ones. And if we look at this picture, so I can maybe draw here by green. I mean that this edge is ending on the one. So if you like draw only the edges that it goes through the ones, then we see that it have like structure of the tree, except for this loop that we have here. All other vertices will be. So if we'd like find all. So if we draw only the edges that finished on the one, then of course we cannot have loop here except for all the ones, because if we just add 1 1 1 1 1, that we can have loop if we don't start with all possible ones. So we have like a tree structure here, and so what we do in our sequence is we start with this edge, and then we just we use orange edges until we can have the orange edge, and we use green ones. And we also again use any orange edge that we can have. And if we cannot go through the orange edge, we go to the green edge. And so I need to explain why cannot we have, so why we already all the times we cannot have a step until we came again to the subsequence. So until we finished here, until we finished in 1 1. And so I think you need to like look at this picture and think about it. So we just go to the orange edge. If we finish the orange, we go to the green, and so on. And what it means that we stuck, that we cannot move. It means that all the green or all the orange edges are already used. But if we used if we used all the green edges, we need to prove that if we use all the green edges of going from this vertex to another, it means that we use all the edges, possible edges from this vertex, because we already use the orange ones. So from each vertex we have one. Here we have like one green and one orange. And if we use all orange, need to be explained that if we use all orange, that we cannot go through. Okay, so I think so. You need to think about this idea. I think we'll explain it the next time, because I think we finished for the day. But also I need to discuss. So we have 2 lectures more, yeah, on the 2nd of December and the 9th of December. And then we'll have like the shot in 16th of December. Am I right?
Sir, we're hoping to ask you about that. We don't know.
Okay, so I think I will give you, today will be a homework about the planar graphs and the Euler graphs, and the next time we will discuss in Hamiltonian graphs, and so we'll have like 1 more lecture, and I need to check what you discussing with Alexander. And do you discuss like Ramsey graphs or something like that? No?
No, sir.
Okay, I think we'll start with them, and I will give you like homework about Ramsey graphs also, and then I think we'll have like final like exam on final work at 16th of December, and then I will give you so I will evaluate your work and give you like your so I will give you like your degree. Okay.
Sir, I have a question about this graph that you drew with green edges and orange edges.
Yes. Okay.
I
will open it again. It's no problem. Yeah. Okay.
So is this a Euler trail?
Yeah, I want to. So we in our algorithm with 0 is better than 1. We do the following. We start from the 1 1, go through each of 1 1, and then do the same procedure. We go through the if we can go out using the orange edge, we use the orange edge. If we cannot use the orange edge, we use the green edge. This is the algorithm, because I put 0, and if I can 0, I put 1. And it means that so what happens? So what it means that I stuck in some vertex. It means that I already used all paths. So so first of all, if I what happens? If I meet some vertex, I go through the all possible orange edge, and then all possible green edges, and so only to prove that all the time I can move further. So of course, since my graph has in and out degrees equal, then if I so all I need to check is I'm all the time I can use. So if I cannot move through green edge, then I already used orange edge and green edge, and this will be contradiction, because I have like in now degree is equal, and so I can also all the time I can move further. So I think I will give the proof in the 5 minutes of the next lecture.
Yes, sir. What I wanted to ask you about was the in and out degree.
Yeah.
Sir, so 0 0, the vertex 0 0, the number of incoming edges is more than the number of outgoing edges.
Yeah, but when we have a loop, we say that it have 1 out degree and 1 in degree.
Oh, okay, sir.
Because we start from this edge and finish it itself, so we have in and out, and so we can we count this twice, and it's not a problem here. And of course, if we have an error path, if you have a loop on one vertex, you get just looped it and go through this loop, and so it doesn't matter. It doesn't. So if the initial graph has an error circuit, if you add one loop on the one vertex, we can just go through this loop, and so we have an error circuit in new graph.
Okay, sir.
So okay. So I think that's also
Okay.
that's all for today. So if you have no questions, then we can finish.
Okay, thanks, sir. Goodbye, sir.
Okay, bye. Bye. See you next time.
Yes, sir.